Continuing with curve sketching, I'm going to do this one. We have y sketch. Y is equal to x cubed minus 3x squared. Okay, so remember all the steps that you follow in order to sketch a curve. So the first one, step number 1, like we said, is the intercepts. So make sure your intercepts are labeled on the graph. So we start with the x-intercepts. So these are sometimes called the roots. So at the x-intercept, y is equal to 0. So that means we have x cubed minus 3, x squared is equal to 0. So we see that x squared is a common factor, so we take it out. So we have x squared, x minus 3 is equal to 0. So this means x squared is 0 or x minus 3 is 0. So here x is 0 or x is 3. So my x-intercepts rather are 0, 0 and 3, 0. Okay, then the y-intercepts, 1. So at the y-intercept, x is equal to 0. So we'll have 0 cubed minus 3 times 0 squared is equal to 0. So we have, this is equal to 0. So this means our y is 0. So the y-intercept is the same as this x-intercept, the origin. So that is step number 1. Then step number 2, we have our turning points. So the turning points, or sometimes called the stationary points. Okay, so all of that means the same thing. So at the stationary points, we know that dy dx is equal to 0. So we have our function y is equal to x cubed minus 3x squared. Now we're going to differentiate. So we have dy dx. This is 3x squared minus 6x. Okay, then we equate this to 0. So we say 3x squared minus 6x is equal to 0. We divide everything by 3. We have x squared minus 2x. This is equal to 0. Then we see x is a common factor. So we have x is 0 or x minus 2 is 0. So this means x is equal to 2. Now for each of these, we need to find the corresponding y coordinate. So if x is 0, we already know that y is 0. So our first turning point is the origin. And then if x is 0, y is equal to 2 cubed minus 3 times 2 squared. And this gives us negative 4. So our second turning point is 2 and negative 4. That is step number 2. Now, step number 3, you have to determine the nature of the turning points. Okay, so the nature, that means you say it's either a maximum, minimum, or a point of inflection. And to check that, you find the second derivative. So d2y dx2, that just means you take your first derivative and then you differentiate it. We have 6x minus 6. And then each of these x values of the stationary points, you substitute them. And then depending on what you get, you will either say you have a maximum or a minimum. So d2y dx2, when x is equal to 0, we have 6 times 0 minus 6. This is negative 6. This is less than 0. So when you substitute the critical point into the second derivative and your answer is negative, that means you have a maximum turning point. Okay, so this one here is a maximum turning point. Then you do the same thing with the other critical point. When x is equal to 2, we have 6 times 2 minus 6. This is equal to 6. This is greater than 0. That means we have a minimum turning point. Now we notice that none of our turning points is a point of inflection, but we want to be able to check, do we have a point of inflection? Now we know that at the point of inflection, the second derivative is equal to 0. So we equate it to 0 and then find the coordinates of the point of inflection. So we have 6x minus 6 is equal to 0. 6x is equal to 6. This means x is equal to 1. Okay, so if x is equal to 1, we now solve for y. Y is equal to 1 cubed minus 3 times 1 squared. And this gives us 1 minus 3, which is negative 2. Okay, so we have a point of inflection at 1, negative 2. So now that we have all our critical points, we sketch. So remember with the sketch, we said you want to see the x and the y-axis. These must be clearly labeled. Okay, then you plot your points. First, I have the origin here, which is a maximum. So at a maximum, you have something like this. This one here is a minimum. So at a minimum, your curve will look something like that. And a point of inflection, the graph is going to change the what we call the concavity. It's either facing down, then changes to facing up, or the other way around. Okay, and then our intercept is 3, 0. And then we have this 2 minus 4 over here. So we say this is a minimum. This one is a maximum. And you can already see the shape is going to go something like this and go through like that. So we connect the points, make sure it's smooth. Okay. Here, arrows just showing that it goes on forever. It's on. Okay. Change that. Okay, then make sure all the points are labeled. This is 3. That's the origin. 0 there. Our minimum turning point, this is 2 minus 4. Our point of inflection is somewhere here. It's at 1 and negative 2. Okay, and then label the graph. Y is equal to x cubed minus 3x squared. Okay, and then you will get all the marks. So just keep in mind all the steps and follow them. Second one, want to sketch y is equal to x cubed minus x squared. Okay, so we start with the y-intercept. At the y-intercept, x is equal to 0. So we have y is equal to 0 cubed minus 0 squared minus 4 times 0 plus 4. So we have y is equal to 4. So our y-intercept has the coordinates 0, 4. Then for the x-intercept, y is 0. So if y is equal to 0, it means we have x cubed minus x squared minus 4x plus 4. This is equal to 0. Okay, so this one we can factorize it by grouping, it seems like. So with these two, x squared is a common factor. So we have x squared and then we have x minus 1. And here, negative 4 is a common factor. So it's minus 4x minus 1 is equal to 0. So I have x squared minus 4. X minus 1 is 0. And this one, we factorize it using the difference of squares. We have x minus 2, x plus 2, x minus 1 is equal to 0. Okay, so this means that x minus 2 is 0, or x plus 2 is 0, or x minus 1 is 0. So this means x is 2, x is minus 2, x is 1. So your x-intercepts, we have 2, 0, minus 2, 0, and 1, 0. Okay, so those are your x-intercepts. The next thing is the turning points. So at the turning points, the first derivative is 0. So dy dx, this is equal to, in fact, let me write it as y prime. So y prime, I differentiate, I have 3x squared minus 2x minus 4. And at the turning points, y prime is equal to 0. So I have 3x squared minus 2x minus 4. This is equal to 0. And then I solve it. So you can use the formula to solve this. You'll get x is equal to 1 plus the square root of 13 over 3, or x is equal to 1 minus the square root of 13 over 3. So this is approximately negative 0.9. Okay, so I write it only to one decimal place because it's easier to approximate it on my graph. And then here x is approximately 6.1. Sorry, I got that mixed up. This one is 1.53. So it's 1.5. And then this one here is the one that is negative 0.9. Okay, and then we find the y coordinates. So my turning points, they are 1.5 and great. 1.5, 0. And then I have negative 0.6. Those are my turning points. So to get these y coordinates, you just take the 1.5 and substitute it into this equation, and then you can get the y value. Okay, so now that I have my turning points, I need to determine what is the nature of my turning points. So to determine the nature of the turning points, we, excuse me, we use the second derivative test. So y double prime, I take the first derivative here, and I differentiate it, so I'll get 6x minus 2. And then I substitute 1.5 here, and we have 6 times 1.5 minus 2. Okay, this is positive, and therefore we have a minimum turning point. So this is going to be a minimum turning point. And then we do the same thing, y double prime of negative 0.9. So we have 6 times negative 0.9 minus 2. This is negative 7.4. So this is negative, and therefore we have a maximum. Then we want to check, do we have any points of inflection? So at the point of inflection, y double prime is 0. So we have 6x minus 2 is 0. So 6x is 2. This means x is 1 over 3. And then we find the y coordinate. If x is 1 over 3, then to get the y coordinate, we substitute into the formula for y. So we have 1 over 3 minus 3 squared minus 4 times 1 over 3 plus 20 over 27. Okay, so we have 70 over 27. This is 70 over 27, which is about 2.59. So 2.6. So it's approximately 2.6. So again, I round off to 1 decimal place just so I can plot it more accurately. So my point of inflection will be 0.3 and 2.6. Okay, so now I have all my turning points and I'm ready to plot. Okay, so now for the sketch. Remember all those things that must be shown on the sketch. The x-axis labeled, the y-axis labeled. I have my intercepts. Then I have a maximum turning point at negative 0.9, 6.1, so it's somewhere here. And then 4, 0, 0, 4, sorry, is an intercept. And we also have a minimum here. Okay, so you can see the graph is going to go something like that. So this one will be afterwards. So you want your graph to be as smooth as possible. So go something like that. So this maximum turning point, now we can label it. This is negative 0.9, 6.1. This is 4. This is negative 2. This is 1. This is 2. And then minimum here, this is 1.5. 0.9. And write y is equal to x cubed minus x squared minus 4x plus 4. So that is how we sketch that one. Then one more, 3. We have y is equal to minus 4x cubed plus 3x squared plus 6x. I want to sketch this, so we start with the intercepts again. So our y-intercept, so x is equal to 0. So we will have our y is equal to 0. So our y-intercept is origin. And then for the x-intercept, we have x is equal y is equal to 0. So we have minus 4 x cubed plus 3x squared plus 6x is equal to 0. So x is a common factor, so take it out. Minus 4x squared plus 3x plus 6 is equal to 0. Okay, then this means that x is 0 or minus 4x squared plus 3x plus 6 is equal to 0. So this is a quadratic equation, and to solve it, when we solve it, we get x is equal to 1.7, this is approximately, or x is approximately negative 0.9. The y-coordinate here will be 0 in both cases. Because these are x-intercepts. So we have the origin 1.70, 0.9, 0. Okay, then our turning points. Remember, at the turning points, y prime is equal to 0. So we differentiate. I have minus 12x squared plus 6x plus 6. And then we equate to 0. So we say minus 12x squared plus 6x plus 6. This is equal to 0. You can divide everything by negative 6. 2x squared plus x plus minus. This is equal to 0. This leaves us with x minus 1. 2x plus 1 is equal to 0. So we have x is equal to 1, or x is equal to minus a half. The y-coordinate here is 5. The y-coordinate over here is negative 7/4. Okay, so our turning points 1.5 and minus a half minus 7/4. Okay, then the last thing before we sketch, this is the nature of the turning points. So find our second derivative, minus 24x plus 6, and then we substitute. I put 1 here, I have the minus 24 times 1 plus 6. This is equal to negative 18. This is less than 0. This means we have a maximum. Then y double prime of minus a half. This is minus 24 times minus a half plus 6. This gives us 18. Positive, and therefore we have a minimum. So 1,5, this is a maximum turning point, and this is a minimum turning point. Okay, now we just need to sketch. So again, make sure your X and Y axis are clearly labeled. Okay, then we have our intercepts, -1. We have the origin, and then we have 1 at 1.6. We have a minimum somewhere here, maximum somewhere there, and you can see that the curve is going to go so. So just connect the dots. Okay, one thing I forgot is the point of inflection. I do need to show that. So at the point of inflection, y double prime is equal to 0. So it was 24x plus 6 is equal to 0. This means that 24x is equal to 6, x is equal to 6 over 24, which is 1/4. And then the y coordinate, that substitute x equal to 1/4 into the formula. Number 8. That's just so somewhere here it stops facing up and starts facing down. So label all the critical points. Y is equal to -4x cubed plus 3x squared plus 6x. This point here is -1. Here I have -1/2 minus 1.75. Origin, here I have a quarter and 13.8. My maximum is at 1.5, and this intercept is at 1.66. Okay, so that is how you sketch the curves. Okay, our next section is on problems concerning optimization. That's maxima and minima. So what we will be doing in this section is basically trying to find the maximum, whether it's maximum volume, maximum area, or the minimum cost, or something like that. And this we want to do by differentiation. So here's an example of one such problem. So a farmer keeps cattle in a rectangular enclosure. He uses fencing for 3 sides and a long wall on the 4th. If he has 200 meters of fencing, find the greatest area that he can enclose. So with these questions, first thing you need to do is draw a sketch. So he has a wall over here. So this is the wall. And what he wants to do is fence off some area here. In this area here, he wants to have the maximum amount of area. Okay, so we don't know what length these length and width are, so we call this one X and we call this one Y, and then this means this is also equal to X. Okay, so we do know that the area, if we were to work out the area of this rectangular enclosure, it's X times Y. Now, we can't differentiate this one exactly because these 2 variables, because X and Y can both change. They can change depending on if he wants to make it really long or really short. So they're both variables. So what we need to do is write one of the variables in terms of the other and then substitute and have only one variable to differentiate with respect to. So what are we told? We are told that he has 200 meters of fencing. That means the distance from there to there plus this one from there to there plus this one from there to there cannot be more than 200. It must be 200. And if he wants to make the greatest area, he obviously has to use all the material that he has. So if he uses less than 200 meters of the fencing, he's not going to get the maximum area that he can possibly get. So we say that X plus Y plus X, this is equal to 200, or 2X plus Y is equal to 200. And then we see that Y is equal to 200 minus 2x. Okay, then we take this and substitute it in there. So we'll get A is equal to x multiplied by 200 minus 2x. Okay, so this leaves us with A is equal to 200x minus 2x squared. Okay, now one thing you should take note of, and maybe you've noticed from the graphs that we were sketching, the maximum point, at the maximum point, the derivative, the first derivative was 0. At the minimum point, the first derivative was 0. So even in this, if we want to work out the maximum will take place or will happen when the first derivative is 0. Okay, so we find dA dx, and this is 200 minus 4x. And then at the maximum area, we have dA dx is equal to 0. So this means that 200 minus 4x is equal to 0. So 4x is equal to 200, and this means that x is equal to 50. Okay, so if x is equal to 50, this means that y is equal to 200 minus 2 times 50. So this is 200 minus 100, which is 100. Now, we always want to verify and see, does this in fact give us the maximum area? And we test using the second derivative. Okay, so to check that this is a maximum. We use the second derivative. So we find d2a dx2. This, we differentiate the first derivative, which is -4. Sorry, it's this one. Okay, this gives us -4. Okay, so this is negative, so that means d2a x2 when x is equal to 50. This is still going to be -4 because this is a constant. This is less than 0, and therefore we do in fact have a maximum. Okay, and now we want to answer the question. It says find the greatest area he can enclose. So the area, we said, is x times y. We have x is 50, y is 100, and this is 5,000 meters squared. You can say the greatest area you can enclose is 5,000 meters squared. Okay, so follow all the steps that I've done whenever you're solving an optimization problem. So first, draw a sketch, come up with equations. If the equation of what it is you're trying to maximize or minimize is in terms of two variables, you need to rewrite it so that one variable is in terms of the other, and then you can substitute back. Then to find the maximum or minimum, you always differentiate. The maximum and minimum always happen when the first derivative is 0. Then check that it is in fact a maximum or minimum using the second derivative, and then answer the question with a sentence. Okay, next one. A rectangular tank is made of a thin sheet of metal. The tank has a horizontal square base of side X and no top. When full, the tank holds 500 liters. Show that the area A centimeters squared of sheet metal needed to make this tank is given by this formula. Then B, find dA dx and calculate the value of x for which the first derivative is 0. Show that this value of x gives a minimum value of A. Then find the dimensions of the tank with minimum surface area. The first thing, as always, is draw a sketch. So you're making a rectangular tank. This looks like a cube or cuboid. Like that. So we're told it has a square base. So at the bottom here we have x, and this one we can call y, which is height. So we are told it holds 500 liters, so that's the volume. Okay, so 500 liters is the volume, and we know how to convert 500 liters into centimeters cubed because x and y are in terms of centimeters. Okay, so it says show that the area A squared of the sheet metal needed to make this tank is given by this. So we want to find the area. So here we have the front, the back, the two sides, and the bottom. It says that there is no top. Okay, so we don't count the top. So our total area, this is given by the base, the bottom is x squared. The front is xy. The back is also xy, so I have 2 xy. That's the front, the back, and then the two sides are also xy, so it's 2 xy. All right, now what we want to do is write this in terms of x only. So we use the formula for the volume. The volume, this is x squared times y because it's length, base, and the height. Okay, length, breadth, and the height. So that's how we get this one. And then the volume, this is 500 liters. So 500 liters, multiply it by 1,000 to change it to centimeters cubed. So this is okay, so we have 500,000. So we have 500,000 is equal to x squared y, and then we make y the subject of the formula. This is 500,000 over x squared, and then we'll come and substitute it over here. So this is actually just x squared plus 4xy. Okay, so our area, this is x squared plus 4x, and then y, you rewrite it in terms of x. We have 5,000 over x squared. Okay, so this gives us x squared. This x and one of those will cancel, and 4 times 500,000 is 2 million. That's 2 million over x. Okay, so that is A. We have shown that the area is given by this. Now we have to find dA dx. So this was A. B, we have dA dx. So we just differentiate. This is 2x. And here, remember, you can write it as x to the power of -1. So you have negative 2 million over x squared. Okay, that is our derivative. Then calculate the value of x for which dA dx is equal to 0. So if dA dx is equal to 0, that means we have 2x minus 2 million over x squared. This is equal to 0. So this leaves us with 2x cubed minus 2 million equal to 0. Divide by 2. So we have x cubed minus 1 million is equal to 0. So x cubed is equal to 1 million, and x is the cube root of 1 million. Which is 100. Okay, so x to 100. So that's what the question said. Find the first derivative and then the value of x for which dA dx is equal to 0. Show that this value of x gives a minimum value of a. So for a minimum value of a, we have to use the second derivative. So keep that in mind. Whenever you're finding minimum or maximum, it's tested using the second derivative. So we find d2a dx2. So we differentiate this, we have 2, and then this is to the power of -2. So the -2 will come down, here you'll get a positive. So you have 2 million times 2. This gives 4 million over x to the power of 3. Okay, and then we're going to substitute 100 here. So d2a dx2, when x is equal to 100, we have 2 plus 4 million over 100 cubed. And this gives us 4. 2 plus 4 is 6. 6 is greater than 0. Therefore, it is okay. So we have shown that. Then find the dimensions of the tank with the minimum surface area. So we know what x is. X is 100, and this is the formula for y. So we just need to find y and then write a sentence answering the question. So C, x is 100, and y is 500,000 divided by 100 squared. So this gives us y is equal to 50. And then just write a sentence. Find the dimensions of the tank with minimum surface area. So the tank has square base of 100 centimeters by 100 centimeters and a height of 50 meters, or